We're now going to talk about how the Java Completable Futures framework and the various capabilities it provides maps onto the reactive programming principles that we outlined in our initial video as part of this section in the course. So Java Completable Futures map onto the various reactive programming principles as follows. So if you recall, the first principle we talked about was being responsive, meaning that you don't want to block for any length of time. You don't want to block the calling code because blocking leads to underutilization of the available processor cores. It impedes the inherent parallelism in the system. And of course, it also complicates program structure. So there's lots of bad things that happen with blocking. So this will be non-blocking. There's a number of methods that are defined in the Completable Futures API that help avoid blocking. And these include some of the factory methods like supply async and run async, which start up computations to run asynchronously. Various completion stage methods like then apply async and then combine async. Those all will run asynchronously. And also various arbitrary arity methods like the all of and any of methods. And all these things allow the program to continue running, doing other types of processing while background computations are taking place asynchronously relative to the main thread of control. Another way to make your code more responsive is to avoid changing threads unnecessarily. And the issue here is that while using lots of threads can be good, it also has a downside. And the downside is that if you are not careful and you move computations between threads too frequently, you can end up incurring additional overhead from things like synchronization, context switching, memory management, and cache management. So it's kind of like avoiding changing lanes too much if you're in a crowded interstate. If you change lanes all the time, it actually can slow things down because people have to brake and wait for someone else to merge, and it just gets to be dangerous and accident prone. The way this is done, the way you get control over whether or not you change lanes or change threads in the Completable Futures framework is by using various methods defined on the Completable Futures API. So there's a bunch of methods, especially for completion stages, that have the word async after them, and they can change threads. And then there's always equivalent methods that don't have the word async after them, and they don't change threads. So you get quite a bit of control over this. And the underlying Java fork join pool also tries to be very clever about not changing threads unnecessarily. And so it tries as much as possible to do run to completion in order to be able to get the computations to finish, and only does thread changing when things like work stealing are put into effect. In terms of resilience, which is designed to make the program continue to operate even if some operations fail, the way that this works under the hood with the Completable Futures framework is by the so-called exception methods. And these exception methods are designed to decouple the error handling or the error processing from the normal operation processing. So errors are handled in a different way than the normal processing of events. And what happens here, of course, is that you can put in the exception methods where you need them. And if something goes wrong and the exception is thrown, then control is automatically transferred to the appropriate exception handling method, which will catch that exception and do something in response to it. Different things you can do. You can continue to propagate the exception. You can swallow the exception. You could terminate the thread. There's a bunch of different things you can do to cause things to work properly. Note, by the way, that completable futures are always localized to a single process, not to a cluster of computers, much the same as with Java parallel streams. Java parallel streams are designed to run within a process, taking advantage of the various cores in that process. And the same thing is also true of completable futures. They're designed to run in a process, not across a cluster. If you want to use cluster techniques with Java, you would want to take a look at something like Hadoop or Sparks, which gives you better control over cluster computing. With respect to elasticity, the asynchronous computations can run scalably in a pool of threads atop a set of cores. Once again, elasticity here is relating to a single computer, not a cluster of computers. And this is done, of course, in a way that's largely invisible by default by using the common fork join pool. So common fork join pool is the default execution context for running asynchronous operations in the Completable Futures framework. And as we've seen before a number of times, the common fork join pool works nicely because it can essentially take advantage of all the different cores on the computer with a global scheduling model where all the available computations, including those running with any parallel streams that happen to be sharing the same process, all being scheduled by the same scheduler in the context of that common fork join pool. You can also define your own thread pools. You can also define your own fork join pools, but common fork join pool is typically the one that gets used by default. And then the final principle we talked about before, which is this message-driven principle, which I mentioned earlier, is really more of an implementation detail. Under the hood, this is done by the way in which Java's fork join pool is implemented. It work, and actually, for that matter, other thread pools too that come out of the box with Java. They work by passing messages around from one thread to another, and in the case of the fork join pool, doing work stealing that moves messages from one thread's deck to one worker thread's deck to another worker thread's deck, and so on and so forth. There are other aspects of the underlying implementation of the Completable Futures framework that also involves message passing. And we'll take a look at this when we look under the hood at some of the implementations of factory methods that are provided as part of the Completable Futures framework. And you'll see how it's all based on asynchronous message passing under the hood. So what's kind of cool about this is you get a nice method-oriented API or a facade. That's how you program Completable Futures from a programming point of view. But internally, it works by passing messages around, which gives you lots of flexibility and allows the system to kind of auto-scale and optimize itself and be more resilient. So that's the end of the overview of how Java Completable Futures map onto the reactive programming principles. We will talk in more detail later about the richness of different support for reactive programming in Java. And that'll give you a more holistic view of how all the other stuff we've been talking about fits and compares and contrasts with Completable Futures.